Alright, so first off, were there any questions on section 8.2? Excuse me. Alright, so today we're going to do section 8.3, and if time is permitting, we'll get started on 8.4 as well. 8.3, we're looking at trigonometric integrals, and in this section it's really a focus on how to integrate when we have a combination of sine and cosine raised to different powers in the same equation, which you can see here, sine to the m and cosine to the n multiplied together. And same thing with secant and tangent, and just looking at how we would approach those particular types of integrations. Okay. All right. So the first one we're going to look at is the sine-cosine product. Okay, and it turns out here, depending on the values of m and n specifically, this is going to inform us on how to proceed. So there's different scenarios we have to examine. So the first scenario I want to look at is if either m or n is odd. Okay. Now it's possible that both of them are odd. That would also fall into this scenario. So either m is odd, n is odd, or both are odd. Okay. So the other scenario is they're both even. Neither one is odd. So there's two scenarios here that we need to examine. So if either m or n is odd, we separate the function with the odd exponent into two terms. One, just a single function, and the other with the remaining number. Now, what I mean here, let's say, for instance, we have sine to the fifth of x That means we want a single sine x by itself, and the remaining 4 sine x's we'll put together as a separate term. Okay, so we get a single function sine x, and the other, we split it into 2 terms, one with just a single function and the other with the remaining number, which would be the other 4 that are still left over from the original 5. Okay? Or if we had like cosine to the 7th of x, we would say, okay, cosine x times cosine to the 6th of x. If both of them have odd exponents, we only need to do this to one term, not both. So if both have odd exponents, we only need to split up one of the 2. So it may be that we have both sine to the 5th and cosine to the 7th in our expression. We only need to do this for one or the other. We don't want to do both because it's actually counterproductive in this sense. And I'll talk about why when we actually look at an example. The way that we proceed from here, that's just kind of an aside there. The way that we proceed from here is that once we split up one of the trig functions into these 2 pieces as we described here, we then substitute for the term that we did not split up. We then do a U substitution No, sorry, I'm missing a step. Sorry. So now, after we split up one of our terms, that means we have a single sine function and then an even number of sine functions. Because again, if we have an odd number and we take away 1, we should have an even number left over. Odd number, take away 1, we have an even number left over. Whichever one we do, that's going to happen. With that even number of terms left over, we use the Pythagorean identity to replace them and turn them into the other trig function. So with the even number of terms remaining from the one that we split up, use either sine squared x equals 1 minus cosine squared x, or cosine squared x equals 1 minus sine squared x for each sine squared or cosine squared. Okay. And the idea there is that if we took our sine to the 5th, we split it up as sine x times sine to the 4th. Sine to the 4th we would then make sine squared times sine squared and change each of those into 1 minus cosine squared. Okay. Or, if our problem had cosine to the 7th, then we decided to split up that term into cosine times cosine to the 6th. Cosine to the 6th is then cosine squared 3 times, and we would make each of those cosine squares into 1 minus sine squared. Okay. Then once we complete that, we can substitute for the term that we did not change. Yeah. So once we finish splitting up and separating terms, or substituting, splitting up and substituting, we do a U substitution for the term that we did not split up. In this case, either u equals sine x or u equals cosine x. Okay, this should hopefully make more sense once we look at some examples and what we're trying to say here. So let's go ahead and do that. For instance, we have sine cubed x times cosine squared x dx. Now, sine cubed, that's our odd exponent. And so that's the term that we're going to split up. So sine cubed x will equal sine x times sine squared x. And sine squared x will replace with 1 minus cosine squared x. Okay. So doing that, okay, we took our sine cubed, we split it into sine times sine squared. Sine squared we made into 1 minus cosine squared. Filled that back in, and now we're going to substitute for the one that we did not touch, which was the cosine squared. But we want to make sure we just let u equal cosine x, not the cosine squared. We don't want the exponent on that u substitution. The reason that this works is, okay, this is u squared, this is u squared, and then our derivative of cosine is negative sine x dx. By taking all but one of our sine functions and changing them into cosine functions, we can replace all the cosine functions with u, and then sine x is now part of du. Because the whole goal of doing a u substitution is to put everything into terms of u rather than x in this case. Now, we do have an extra negative here, so we'll just make sure we use negative du is sine x dx. Okay. So, split up the sine cubed, sine x, sine squared, change sine squared to 1 minus cosine squared, and then we didn't touch cosine originally, so that'll be our u substitution. And so du is negative sine x dx, and we do get the extra minus sign, which I'll put negative du replaces sine x dx. So sine x dx is a negative du. And then cosine is our u, so this would actually be 1 minus cosine squared, or so 1 minus u squared, and then another u squared here. Okay. So by that substitution, we're actually able to change the integral into a polynomial. Okay, if we will have to go ahead and multiply out at whatever we have left over at this stage. And for instance, here we'll have u squared minus u to the 4th du after we distribute. Okay. And so continuing that integration, u squared integral is u to the third over 3, and u to the fourth becomes u to the 5 over 5, and plus c. We do have to remember that we have a minus sign here, so if we want, we can make it a minus u cubed over 3 plus u to the fifth over 5. C is always positive, there's no need to change that sign. Until we actually solve for the value, we don't worry about it. Now our last step, of course, is to whatever plug back in whatever our u substitution was for, which that was cosine of x. So we'll make this negative cosine cubed x over 3 plus cosine to the fifth of x over 5 plus c. The key in being able to complete this u substitution is that we have to figure out where our du is going to be. We can easily plug in u equals something and make a substitution, but unless we have du accounted for, it's not going to work. So by separating a single sine variable and changing everything else to cosines, then that sine will be part of our du, and then the cosine will just be our u in that case. Okay. Let's do one more example before we look at the other case. Now in this example, both of the exponents are odd. Both of them are 5 in this case. So we could reasonably split up either of these two trig functions. Since we split up sine x before, let's split up the cosine x this time. Okay, so we could split up either one since both are odd. Well, this time let's try cosine to the fifth. So we'll say cosine to the fifth of x is equal to cosine x times cosine to the fourth of x. Now cosine to the fourth is cosine squared of x times cosine squared of x, and then each of those cosine squares will make into 1 minus sine squared of x. Okay, so that'll be our substitution for cosine to the fifth. Now here, if we like, we can take 1 minus sine squared and 1 minus sine squared and make it 1 minus sine squared in parentheses square, since there's two of them. But we certainly have one single cosine left over by itself. So our sine to the fifth was unchanged. Now we have a single cosine x, and then we have 1 minus sine squared of x twice dx. Again, our reasoning is by leaving off this one term of the cosine and then changing the rest into sines like we did, sine squares specifically, again, it makes every single term in this integral a sine term, sine to a power, except for a single cosine term by itself. We didn't touch our sine to the fifth, so we'll let u equals sine x, and then the derivative of sine x is cosine x. And again, this is why it works, because now we just have this single cosine x dx left over, and that'll be our du. And since u is sine x, this will be u to the fifth 1 minus u squared in parentheses squared. Okay. Now again, this is a polynomial. We do have to work a little harder in this case just to complete the integration because there is some algebra that we need to do. We'll have to square this binomial and then distribute the u to the fifth, and then we can integrate. So, squaring the binomial, so we get 1 minus 2u squared plus u to the fourth. And then if we distribute our u to the fifth, we get u to the 5 minus 2u to the 7 plus u to the 9 du. Now we can complete our integration, and once we complete that, we'll resubstitute for u equals the sine x. So u to the 6th over 6. Now this would be 2u to the 8 over 8. I'm just going to go ahead and take that 2 over the 8 that would be on the bottom and just reduce it to a 4. And then plus u to the 10 over 10 plus c. And finally that would be sine to the 6th of x over 6 minus sine to the 8th power of x over 4 plus sine to the 10th power of x over 10 plus c. And that would be our answer. Okay. In both problems, we basically did the same process, although our focus in one problem was on one function and our focus on the other was on a different function, but the same process works. Again, we started with sine to the fifth, cosine fifths, and this time we could have used either one to split up because they both had odd exponents. This time we tried cosine to the fifth instead, since we did sine in the previous example. So cosine to the fifth was cosine times cosine to the 4. Cosine to the 4 is cosine squared times cosine squared, which we made each of the cosine squareds into 1 minus sine squared according to our identity. Then, because we have everything in terms of sine except for that single cosine, we can let u equal sine x, and then du would be that lone cosine x that we have left over. From there, we turn everything into powers of u, since sine raised to the power becomes u raised to that power. And then we just have to work out what the polynomial is from there, and then integrate, and then replace at the end. Okay? Alright, so the other scenario we want to look at for sines and cosines is the case where m and n are both even. It's really there's 4 outcomes when we have these exponents. Sine may be even or odd, and cosine may be even or odd. And as long as one of the two, or both, are odd, then we can use that first approach that we just looked at. But there is one scenario where neither one is odd, and that's where they're both even then. Okay? If they're both even, it's actually an entirely different process. The key identities that we use here are what we refer to. I misspelled identities. I left out a syllable, sorry. it doesn't look right. Yeah, it's fine. So our key identities are called the power reducing identities. I'm just forgetting everything now. Sorry. Anyway, let's get to the formulas. I can regurgitate those easily. Cosine squared of x. Our identity that we use here is 1 plus cosine of 2x over 2. And then sine squared of x is equal to 1 minus cosine of 2x over 2. Now, these two formulas are basically, they're based on the double angle identities for cosine of 2x, but we've solved them for different terms instead. This first equation comes from the fact that cosine 2x is equal to 2 cosine squared x minus 1. And what we've done is we've solved it for cosine squared x. Okay, we add the 1 over and then divide by 2. Okay. The second identity comes from the fact that cosine of 2x is equal to 1 minus 2 sine squared of x. And again, to solve for sine squared, we subtract the 1 over and divide by negative 2, which changes the signs here on top. So, anyway, so these are our double angle identities. And that's the source for these identities that we call the power reducing identities, or power reducing formulas. What it does, and the reason we call it power reducing, is it takes something with the square exponent, and now it has just a linear exponent. This is cosine to the first. Even though the angle inside is more complicated now, it's still something we can integrate. And the issue is we can't just integrate cosine squared by itself. We can integrate cosine to the first, or just regular cosine, but we cannot integrate cosine squared just by it the way it is. Okay. And the same is true for sine squared. We can't just integrate sine squared. However, if we use this identity, we simplify it to where it's just a linear trig function rather than a quadratic trig function. If that makes sense. And so we do this, we use this identity for each cosine squared and sine squared in the integral. And then we just keep going from there. Okay, we just repeatedly apply these until we get to a point where we can actually integrate what remains. Okay? So what I wanted to demonstrate this with as an example is, let's just look at the integral of the product of sine squared x times cosine squared x. Okay. So for both of these, we want to plug in our power reducing formulas, which is for sine squared, we know that's 1 minus cosine 2x over 2, and cosine squared we know is 1 plus cosine 2x over 2. Okay. Now we have 2 times 2 in the bottom. I'm just going to make that a 1/4 on the outside so we don't have to worry about it. We do have 1 minus cosine x times 1 plus cosine x, which creates a kind of a difference of squares situation. Like if we have 1 minus x times 1 plus x, is 1 minus x squared as the product. So technically we do FOIL these together, but part of it cancels itself out. Now the issue here is that after multiplying these numerators together, we still have a cosine squared x in the equation. We're going to have to change that with another power reducing identity. Okay? Now, for cosine squared 2x, we'll make that 1 minus cosine of 4x over 2. Okay? So, let's point out what's happening here. Whenever we apply our power-reducing identity that we talked about here, we notice that the angle doubled. So cosine squared x became 1 plus cosine of 2x over 2. So here, where we have cosine squared of 2x, and we apply the power-reducing identity, we get, actually that would be a plus, I'm sorry, because cosine's a plus and sine's a minus. But we get 1 plus cosine of 4x, because again, the angle doubles when we reduce that power. Okay, using this formula specifically, I mean. So it's 1 plus cosine 4x over 2. Now, once we get it here, we no longer have any squares in our expression inside the integral, so we should be able to simplify and then just integrate from that point. Okay. We have 1, and this will be minus 1 over 2, and minus 1/2 cosine 4x dx. So we'll go ahead and combine 1 minus 1/2 into a 1/2. Now at this point, let me get this out of the way. At this point, if we wanted to factor out another 1/2, that would be completely fine. In fact, if we want to go ahead and do that, from both of these terms and pull it outside, or make a 1/8 outside, we just have 1 minus cosine 4x. That particular step is not strictly necessary, but it does make the integrations inside. Not that they were terribly difficult before, it makes them a little bit easier. But if we go ahead and proceed with our integration, integral of 1 is x, and the integral of cosine 4x is 1/4 sine 4x. And then we can just distribute our 1/8 back and they'll have our answer. Okay. So that's how we would handle the case where both of the exponents are even on the sine and cosine functions. So to sum up, with even exponents, we just use our power-reducing identity, or identities, to reduce them down to where we finally get to a point where we can just integrate a basic cosine or basic sine function. Actually, it should just be cosine each time, because even if we have a sine squared, it's going to become a cosine. Okay, so by the end, we should anticipate having to identify cosine of something times x, which is always 1 over that coefficient times sine of that same angle. Okay, that's generally how these proceed. Now, depending on the complexity, like if we had sine to the 4th, cosine to the 4th, this would be a much worse problem, because we'd have 2 of these and then 2 of these. We have to multiply all of those together, and we'd have to keep, we'd have to keep simplifying these cosine squared terms down to here, and it just get worse and worse. probably for our exam, I'll give you one where we have the odd one, at least one of the terms has an odd exponent rather than this double even one. But I wanted to show all the scenarios. Okay. And again, with our odd exponents, the key is, as long as one of them has an odd exponent, we can split that up into a single term and then a combination of squares, which then are converted to the other term using identities. Specifically, the cosine squared plus sine squared equals 1 identity, or the Pythagorean identity as we refer to it. Okay. That takes care of sine and cosine. So let's move on to the secant tangent combinations. Which, according to my structure, I think is B. Okay. Now this one we'll find is very different from sine and cosine, because sine and cosine we were just looking for which one was odd and going from there. And it's similar here, except secant and tangent don't, if we think about the derivatives of these functions, we know the derivatives of sine and cosine are pretty straightforward. Derivative of sine is cosine, and the derivative of cosine is negative sine. It's a little more complicated when we think of secant and tangent, though. The derivative of secant is secant times tangent, and the derivative of tangent is secant squared. Now, the process, or the goal that we have here is to kind of isolate, one of the, a set of terms to be du, and then everything else becomes u. It's really the same thing we were trying with the odd exponents in sine and cosine. But like I said, because the derivatives are different for secant and tangent, it does work out slightly different. So case 1, let's say that we have, for case 1, what do we want to use? Let's say we have an even number of secants. Okay. If we have an even number of secants, so m is even basically, in this case we split up secant to the mx into as many secant squares as we can get. For example, if we have secant to the 6th of x, then we'll make 3 secant squares out of that. Then we leave one secant squared x alone, and then use secant squared x equals secant squared x equals tangent squared x plus 1. Yes, that's correct. Yeah, and we use secant squared x equals tangent squared x plus 1 for the others. Okay. So, for example, if we had secant to the sixth of x, we make it secant squared x times secant squared x times secant squared x. And we would change two of our secant squares into tangent squared x plus 1. And leave one secant squared x alone. The reason we do that is then we can let u equals tangent x and du equals that extra secant squared x dx that we have left over. Okay? Because the derivative of tangent is secant squared x, we're trying to get a single secant squared x by itself, and everything else in the problem will then be in terms of tangent, which we're going to replace those with our u. It's really the same principle we were using in the odd number of sines or cosines process. The only difference is the different complexity of the derivative of tangent being secant squared. Okay. All right. Let's work an example for that one. So we have tangent to the fourth of x secant sixth of x dx. So we have an even number of secants. So secant sixth of x, as we said, secant squared times secant squared times secant squared. Change two of those into 1 plus tangent squared, or tangent squared plus 1. The order is not important. And leave 1 secant squared x unchanged. So what that gives us now is we still have our tangent to the fourth x that we started with. We didn't mess with that term at all. And then our secant 6, we've now changed it to 1 plus tangent squared x. And we have two of those, so we can actually write it as a square if we prefer than two separate terms. And we also have a secant squared x dx. Again, secant squared is the derivative of tangent, so we'll let u equals tangent x and du equals secant squared x dx. So that means if u is tangent, then tangent to the fourth will become u to the fourth. Tangent squared is u squared. And then secant squared dx, all of this right here, is du. Okay. Again, like we had seen in previous problems, we work this one out algebraically, multiply everything out, and then we can integrate. So we square the binomial first. We distribute. And finally, we can integrate. So 1/5 u to the 5 plus 2/7 u to the 7 plus 1/9 u to the 9th plus c. And finally, just plug in our original u, which was tangent x. So 1/5 tangent to the 5th of x plus 2/7 tangent to the 7 of of x plus 1/9 tangent to the 9th of x plus c. If you really want to challenge, take the derivative of this term and try to simplify it to what we started with in our integral. It gets a little weird, but it does work. Okay. So that's our even number of secant cases, or case. So our second case, in this one we actually have 3 different cases for. The second case is an odd number of tangents. Notice that this is already different than when we looked at sines and cosines. In that case, we were looking for the one that was odd. And if they were both even, we had the power reducing formula. For secants and tangents, ideally, we want either an even number of secants or an odd number of tangents. These are the best case scenarios. Okay. If we have an odd number of tangents, we again split up tangent to the n of x into tangent x and as many tangent squares as we can get. Okay. For example, if we had tangent to the 5th of x, we would make that tangent x times tangent to the 4th, and tangent to the 4th would then be split up into tangent squared times tangent squared. We would then change each tangent squared into secant squared x minus 1. That's our, again, one of our Pythagorean identities. Tangent squared x equals secant squared x minus 1. Alright. Okay, and then from there, this is where the use substitution is a little bit different. We also split our secants up into a single secant and then whatever remaining secants we have. Whatever m minus 1 would be equal to. So not only do we split up the tangents, we also separate the secants here. And the reason we do that is because we're going to let u equal secant of x, and du will be secant of x times tangent of x. That's the derivative of secant. Okay. And to accommodate this du, we need a secant and we need an extra tangent. Okay? So we leave one tangent untouched, the others are all changed to secants, and we'll make sure we leave out one secant to be part of that du also. So the real issue we're seeing in case 1 for sine and cosine, and then case 1 and 2 for secant and tangent, is that we're basically trying to set up a u substitution by ensuring we have the necessary du to complete that substitution. And so by peeling off a secant and a tangent from each of those terms, that's going to be our du. Okay. Now, we don't have to do anything with the extra secants because that's just going to be u to whatever power that is remaining. But then each of our tangents have to be changed to secant squared minus 1, and that'll be u squared minus 1 in our substitution. Let me work an example for this one now. So we have secant cubed x times tangent cubed x dx. Now, we have an odd number of tangents. We do not have an even number of secants, so we can only use the second method here. There could be a scenario where we have both an even number of secants, which was case 1, and an odd number of tangents, case 2. And in that scenario, we could choose either method to apply. And we had a similar example with the sine and cosines. In this particular case, with an odd number of secants and an odd number of tangents, we can only use the second approach that we just described. So we have an odd number of tangents. So we're going to make a tangent cubed x into tangent x times tangent squared x. We're also going to take their secant cubed and split it up into secant squared x times secant x. Okay, and we'll leave secant squared alone, but our tangent squared x will become secant squared x minus 1, and we still have our secant x tangent x dx. Okay, so that's where we're at, and basically at this point we're set up for our u substitution. We took away one of our secants, we took away one of our tangents. That's going to be our du. The other tangent squared that we have, though, will make secant squared x minus 1. So we can let u equal secant, so it's be u squared minus 1, and then du. Okay, and so that's exactly what we get. U is equal to secant, so this is now u squared. This is also u squared, and we have minus 1. And then the rest of this is just our du, because it's such a complex term. Okay. So in completing that u substitution, we're able to now multiply together what's left over. And then integrate. And finally replace u with secant x once again. Okay. Are there any questions on those? Now we talked about cases where tangent had an odd exponent. We talked about cases where secant had an even exponent. Now there's a third case we have to discuss. And this is the case where we have an odd number of secants and an even number of tangents. Okay. This is our last scenario here, because there's, again, 4 combinations that could happen with exponents being even or odd for secant and tangent respectively. 3 of them are covered by those first 2 cases. So case 1 we said was secant, even number of secants. Case 2 is an odd number of tangents. Now it's possible that both of those are true. That's our third scenario, and we can use either of those first 2 methods to solve. But what about the case where we have an odd number of secants and an even number of tangents? Well, my advice to you here is good luck. Okay. Unfortunately, there's just not a set process that really works in each of these cases. One example that we looked at last time is the integral of secant cubed x. Okay. And that was from section 8.2, which required integration by parts to solve. And that's one strategy, is that we may have to use integration by parts. We may have to... Another strategy is to turn everything into sines and cosines rather than secants and tangents, and see what we can do there. Sometimes it works out, sometimes it's less so. So there's different strategies we can apply. But really, there's not a set process that we could possibly use every single time, you know. Okay. I'm actually not going to ask you any of those, this third type. I wanted to mention it, though, because it is notoriously difficult. But again, like I said, a secant cubed is one example. If we had tangent to the fourth, that would be another example, which... Just my first thought for tangent to the fourth is split it up into tangent squared, change one tangent squared to secant squared minus 1, distribute the first tangent squared to those, split them up as 2 separate integrals, and tackle them from there. It's not a perfect solution, but I think it would let us get there. And one of those we could use like a integration by parts, and the other the integral tangent squared. Oh, we would just turn that into sines and cosines, and that would work fine. Eventually. No, actually, we could just turn it. We could just use the identity there and integrate both pieces separately. That probably works better. Let me go ahead and work that problem, since I feel like I've talked my way through it pretty well. I'm really hoping that first part works out like I hope. But I just want you to consider this example. And like I said, my strategy, my first thought would be let's take tangent squared x times tangent squared x. Change one of the tangent squared x's into secant squared x. I guess would be plus 1. Yeah. We want to make sure we use the correct identities there. Whenever we get around to a test on this, I will actually let you use an identity page, and probably what I'll do is I'll create an image out of it and include that image in kind of the header for the Canvas quiz that we set up for the next test, which is several weeks away, so don't worry about it just yet. I haven't graded the last one yet, so. But yeah, I'll definitely allow y'all or provide y'all a trig identity sheet. Definitely. So, probably at this point, some of you are a little concerned about that. We're using a lot of these things in this section, and we'll continue to do so throughout a lot of the course. And it's nice if they're second nature, but at the same time, I don't have a problem providing those for you. Okay. So what I said before is let's go ahead and distribute. So we can have tangent squared times secant squared, and then just tangent squared by itself. And my thought was we can split these up into two separate integrals. Oh, this one kind of works out. This one works out nice because now we have an even number of secants. Okay. Actually, this is just a straight u substitution because we know secant squared is the derivative of tangent. We just let u equals tangent x, and du equals secant squared x. Okay. Yeah, that's just the derivative right there. So that's du. And then here's u squared. Okay, and then for the other one, I think the best course is to just take tangent and turn that into secant squared x plus 1. So now both of these are integrable also. So this will be u to the third over 3. Integral of secant squared is tangent x, and the integral of 1 is x. Yeah. And our last step is just change this back. This will be tangent cubed over 3 plus our tangent x plus x plus c. So I guess it's not terrible, although that was a full page of work, so at the same time it's not necessarily the easiest thing. My main point is that there's different ways we can go with this last case, and it's really just down to trial and error, unfortunately. And we just try to figure out what works and go from there. Okay. I suppose it also would have worked in this case if we had taken we had tangent to the fourth. We could have taken both of those tangent squares, like we did up here, make them both secant squared x plus 1, and then FOIL that together. And that way we have an even number of secants in two different integrals. That would work as well. This came out kind of nice, though. All right. So that takes care of section 3. Again, the issue here is just being accustomed to the patterns, and a lot of math is just recognizing patterns and how we deal with them anyway. It's especially important in cases such as this, where if we have sine and cosine, we're looking for the one that has the odd exponent, and we're splitting that up. Or if they're both even, we use the power-reducing identities. For secant and tangent, we either have an even number of secants or an odd number of tangents. We split those up accordingly. And if we don't have either one of those things, then we just do trial and error. That's kind of our summary of how we deal with those things. I think it's especially important in this section that you practice these things and practice recognizing and then working through how each of these problems need to be solved. So, okay. Let's move on to section 8.4. We'll get started on that today. I don't know that we'll finish it today. We'll see how far we can get. Section 8.4 is on trigonometric substitution, which, again, trig is kind of the main topic here. And I know for a lot of Calculus 2 students, this may not be your strongest skill, working with trigonometry, but by keeping at it in these two sections in particular, hopefully that will build our skill. I'm going to teach it a little bit different than the book does. It's actually the same concepts, but rather than boiling it down to being able to recognize a substitution, instead I want to boil it down to kind of a geometric approach. Okay. Let's look at the right triangles before we do anything else. When we talk about a right triangle, and I'm just going to draw a generic one here, we have sides A, B, and C. And we know in this right triangle that A squared plus B squared is equal to C squared. But instead of looking at combinations, let's see what each one is equal to individually. Like, we know if A squared plus B squared equals C squared, then C is basically the square root of A squared plus B squared. If we change this around and say that A squared equals C squared minus B squared, we can say A is the square root of C squared minus B squared. Likewise, we could say B squared is equal to C squared minus A squared. So B is the square root of C squared minus A squared. The point being that depending on if we have a sum of squares under a radical or a difference of squares under a radical, whether the squares are added or whether the squares are subtracted, then that tells us which side of the triangle we're working with. Okay? So what's going to happen is we're going to be looking at integrals that have similar terms to this inside, although they'll have variables certainly rather than just numbers. But it may be that we have like x squared plus 4. We may have x squared minus 4, or we may have 4 minus x squared. There's different ways that we'll express this, but let me say, for example, we have the square root of 4 minus x squared. Okay. If we wanted to create a right triangle where this was one of the three sides, well, we know that if it's a difference of two squares, like we have here, then our square root is actually either side A or side B. The hypotenuse C is always the sum of the square root of the sum of the squares of the other sides. So if we have a difference of squares, that means we have one of the two legs. So anytime we have a difference of squares, I like to put it on the right hand side, and I'll talk more about that as we proceed further into this topic. But I prefer the right hand side to be our square root. And what that tells us then is that the hypotenuse is the first term under that radical. So the hypotenuse is, well, the hypotenuse squared is 4. So that means our hypotenuse is 2. And the other side squared is x squared, so that means our other side is x. So working with this square root of a difference of squares, we can make this one of our three sides of our right triangle and then quickly identify the other two sides based on that. The square root of 4 is 2, and the square root of x squared is x. Similarly, if we have the square root of x squared minus 9, again, if it's a difference of squares, we want to go ahead and put that on the right hand side. And then the square root of the positive term under the square root is the hypotenuse, and the one that's subtracted, its square root is the other leg of the triangle. And again, this is just mirroring what's happening here with these expressions. Okay. Difference of squares means we solve for either side A or B, which is one of the two legs. Now, if we have a sum of squares, let's say we have x squared plus 1, and we want to create a right triangle, we know if we have a sum of squares, that's going to be our third side, our hypotenuse. So we'll actually put square root of x squared plus 1 here. That means one leg is x and the other leg is 1. I usually put the variable on the right hand side and then our constant on the bottom. Okay. That's the kind of process we want to utilize here, and this will be part of the one of the interesting things about this section is that we'll have problems where there's no trig in the problem to begin with, and there's no trig in the problem to end with, depending on how things go. And but we completely use trigonometry in the middle of the problem to actually help us solve it, which is interesting to me. Anyway. The idea is that if we have one of these expressions in the problem, we want to construct a right triangle where that expression is one of the three sides. Whether the x is subtracted from the constant, or we have a constant subtracted from the x squared, or they're both positive, which means it's on the hypotenuse. Okay. That's kind of the patterns we're looking for. And notice that if we square this side, and we square this side and we add them together, then we get the third side squared. Because if we square the square root, it's just 4 minus x squared. We add the x squared to that, which is 4, and that's identical to the hypotenuse squared, which is also 4. The same is true for all of the other constructions that we did. So if we have a difference of squares where the constant is first, constant, x, square root. A difference of squares where the x is first, we have x, constant, square root. And a sum of squares, so we have our square root, x on the right hand side, constant on the bottom. Now, the reason I want our square roots on the right hand side, or if our square root's on the hypotenuse, then just the x on the right hand side. Setting it up this way means that when we use our trig substitution, we're going to be working with secants and tangents rather than cosecants and cotangents. And I encourage you to do the same. I'm not saying it, I mean, the two sides of a triangle, these are interchangeable as far as how we designate them. So it's really not a big deal. But the reason I stress that we put it this way is, if we're going to label this side as theta, or the angle there is theta, if we want to look at combinations of sides, we're going to look at opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Well, what if we have something like this where it's hypotenuse over adjacent? Well, that's secant. If we have if these two sides are switched, it'd be a hypotenuse over an opposite, which is cosecant. Okay. So we have to be careful. The reason I would say we prefer secant and tangent over cosecant and cotangent is because the integrals of cosecant and cotangent are negative, and that's just one more level of complexity that we would have to deal with, and that's one at least that we can eliminate from this process, and overall makes it easier. I think we're more most students are more comfortable with secant and tangent than they are with cosecant and cotangent for that reason, because of the negative integrals. So, anyway, so this is kind of the introductory part. This is the setup of it. This is kind of the basis for what we're going to do. Now, these are harder to make problems up for out the top of my head, so I'm going to pick some problems out of the book. And you can see how they've kind of talked about the same thing here. Although, notice that they don't necessarily adhere to the same principle I do. Now, what the book is going to do, if you read through it, rather than using these triangles every single time, they're going to boil it down to a simple substitution and have you use identities instead of the triangles. I prefer the triangles personally because I think it taps more into our knowledge of, like, sine is opposite over hypotenuse, cosine is opposite over, or adjacent over hypotenuse, and tangent is opposite over adjacent. So it taps into that SOHCAHTOA knowledge that we should already have and be pretty comfortable with. Anyway. Okay, let's start off, and I'm just going to work with some even problems out of the book, and then, as usual, we'll have odd problems in the assignment. So let's start with number 4 on page 547. We have the integral of 4 over x squared times 16 minus x squared dx. Okay. Sorry, here we go. So this is the integral that we're working with. we want to create a right triangle, and again, we're focusing on the square root term here. Square root of 16 minus x squared. Create a right triangle. And we said if there's a difference of squares here, we want to make it our right-hand side, our vertical side. And then again, this is a difference of squares, meaning the positive term, that's going to be the hypotenuse, and the one that's being subtracted, that's the other leg of the triangle. And so that would be our setup. Now, the question is, how do we generate a substitution out of this? Well, that's what we need to look at next. So I want to look at, I want to solve for x, basically. I want to get a trig function that represents x. Now, working with this side x, I could say either work with x in the square root, or you can work with x and 4. And I think, generally speaking, x and 4 is going to be much nicer. So we think about relative to theta, x is adjacent, 4 is the hypotenuse. So we know cosine of theta is adjacent over hypotenuse, which in this case is x over 4. Now, what that means is we can solve this equation for x and say x is equal to 4 cosine theta. Okay. So essentially this is going to be our substitution. Let x equal 4 cosine theta, take its derivative, dx will be negative 4 sine theta, d theta. The reason we need to find dx is that we'll replace x with 4 cosine theta. We'll replace dx, so it's in terms of d theta. We also need to find a replacement for the square root of 16 minus x squared. Now, going back to our triangle, we want to work with our angle theta, with our side with the square root of 16 minus x squared, and again with the constant side. So that would be opposite over hypotenuse, which is sine of theta. Okay. And so we can say, based on that, the square root of 16 minus x squared is 4 times sine of theta. Okay. So these are our key terms that we're looking for, because those are all elements that are part of this integral that we're trying to solve. We have x, we have dx, and we have the square root of 16 minus x squared. And so, we take all this information we just gathered and plug it into this integral. The 4 is just going to remain the 4. There's no way around that. X, we said, was 4 cosine theta, and that is being squared. Dx is negative 4 sine theta d theta. And square root of 16 minus x squared, we said, is 4 sine theta. So what we've done with this is we've converted the entire integral into terms of sines and cosines in this case. Depending on which sides of the triangle we end up looking at, it may be different trig functions. Like I said, sines or cosines, or secants and tangents. Which, when I say that, probably that makes you instantly think of what we just talked about in section 8.3. And yes, it's entirely possible that we end up with one of these problems where we have to solve it using the same processes that we just talked about in the previous section. It just depends on where this goes. So it's no guarantee it's going to be crazy. It could actually be a relatively nice integration. So it just depends on what we get. One thing we want to be careful of is like here when we have x squared, we replaced x with 4 cosine theta. We want to make sure we put that in parentheses square so we square both parts of that substitution. That's another thing to watch out for here. Because of that, that means we have 4 and 4 on top, and then we have 4 twice, and then a third time on bottom. 4 times 4, so 16 on top, 4 times 4 times 4, so we have 64 on bottom. So we have basically 16 over 64, so it reduces to 1/4. So if we want to take all of our 4's out and put them together, the other way we could do this is like these 2 4's cancel out these 2 4's, and we have 1/4 remaining. And we also have a negative sign I'm going to factor out as well. So essentially we took all the constants and brought them outside of the integral and just simplified them as best we can in that step. Now we have a sine theta on the numerator, and on the bottom we have cosine squared theta over sine theta, and we can see the sine thetas will cancel out. So we have d theta over cosine squared theta. Can anyone see how we're going to go about integrating d theta divided by cosine squared theta? Or is there a way that we can change that to something that's more easy to work with? Well, one strategy that we have when our trig functions are in the denominator like that is we can use identities to rewrite them as terms in the numerator. When we have 1 over cosine squared, we think about, okay, what is 1 over cosine in the first place? 1 over cosine is actually secant theta. That's the definition of secant. Secant's the reciprocal of cosine. Okay, so if we have cosine squared on the bottom, we can bring that up into the numerator and make it secant squared theta d theta. Okay. Now, what is the integral of secant squared theta? So it turns out the integral is exactly tangent of theta. Integral of secant squared is tangent. So we've integrated the expression, integrated secant squared to tangent, but the problem is we still have tangent theta in our problem. We need to figure out what tangent theta is equal to. Well, for that we can actually go right back to our triangle. Okay, what is tangent of theta? Well, we know tangent theta is opposite over adjacent, so we'll just say tangent theta is the square root of 16 minus x squared over x. And so there's nothing we can really simplify there, although if we wanted to rewrite it as the square root of 16 minus x squared over 4x, that would be appropriate here. And so that would be our integration. Now notice that we started with just x's and square roots, and we ended with x's and square roots, but all the way throughout in the middle we had all kinds of trig functions happening and taking place. And even though the trig was completely necessary, it no way figured into the original question or the ending answer, which is interesting, I think. But it's an important tool in helping us expand the types of expressions we can actually integrate. And what happens here is this is essentially an inverse sine, but there's some other terms here that we have to account for. Okay. So next, let's look at 8, which is the integral of the square root of x squared minus 25, all divided by x. Okay. We can see this one's already different than the last one. Well, it's slightly different because, one, the square root's in the numerator, although it doesn't really change as much as we might think. But the other thing is that instead of having a number minus x squared, we now have x squared minus a number, and that does change how we set up our triangle. We have a difference of squares. Anytime we have a difference of squares, we'll make that our right-hand side, square root of x squared minus 25. Whatever's first and under the radical, and when it's a difference of squares, whatever's first goes on the hypotenuse, and whatever's second goes on the other side, the other leg. So we have square root of x squared, which is x, and square root of 25, which is 5. So that's our setup for our triangle. Now we need to find x. Now x, we want to use 5, so we want hypotenuse over adjacent. So we think about which function is hypotenuse over adjacent. Well, we know adjacent over hypotenuse is cosine. And so what we've done is we've actually had the reciprocal of cosine, which is secant theta. Okay? So hypotenuse over adjacent is secant. It's a reciprocal of cosine. So we can say that x is actually equal to 5 secant theta by multiplying by the 5. Additionally, we can take the derivative of that and say dx is 5 times secant theta tangent theta, d theta. Now we also need an expression for our square root. Now again, we want to pair our square root with the constant. Whether we're solving for x or the square root, we always want to pair them with the constant because we can freely move the constant to the other side to solve for that unknown. So if we have the square root of x squared minus 25 over 5, relative to theta, that's opposite over adjacent, and opposite over adjacent we know is tangent of theta. Okay. And so that means since the square root of x squared minus 25 over 5 is equal to tangent theta, then the square root is equal to 5 times tangent theta. Okay. So we go ahead and substitute in. On the numerator, we have the square root of x squared minus 25, which we said is 5 tangent theta. We have dx, which is part of the numerator. That's 5 secant theta tangent theta d theta. And on the bottom, we have x, which is 5 secant theta. Okay. So again, it takes us a while to develop that substitution, but this is what we end up with. And we're able to replace all of our x's with functions of theta instead. Whether we're using a U substitution or a trig substitution such as this, we always want to convert our variable from one to another entirely. So after we convert here, there shouldn't be any x's left here. Okay? We're now looking at everything in terms of theta instead of x. Alright, now we go ahead and we want to simplify. Now, this one we can see very quickly. 5 secant theta cancels. We have an additional 5, which I'll go ahead and factor out. And then we have tangent times tangent, so we actually just have tangent squared theta d theta. Now, this actually falls into that category 3 for secant and tangent that we basically said, good luck, do your best, and solve the problem. Again, but tangent squared by itself is not bad because we have an identity for tangent squared, which is tangent squared theta is equal to secant squared theta plus 1. The reason that this works is because now we know we can integrate secant squared into just tangent. Okay. Now, for tangent theta, we know that we can just go back to the triangle and find what tangent of theta is equal to. Or actually, we already know what tangent theta is equal to. It's the square root of x squared minus 25 over 5. We use that in the process of solving this problem. But the problem is, what is theta itself? Theta is actually just, it's the angle here. We don't know what that angle is, or do we? Well, it turns out this angle is unknown because, we don't know how long side x is. Okay? So without knowing how long side x is, we don't know the exact value of this angle. It turns out to be a variable angle. But that's okay. As we look here, we said x over 5 is equal to secant theta. So one more thing here, if x over 5 equals secant theta, how do we solve for theta here? Well, if we have a secant of theta, then we take the inverse secant of both sides, and the inverse secant cancels out the secant, and we just have the inverse secant of x over 5. If we like, we could change that to the inverse cosine of 5 over x. Okay. Again, due to the reciprocal nature of secant and cosine, we would just flip over those terms inside. So we could use either one of those. If we want to go ahead and write inverse secant of x over 5, that is entirely applicable. Okay. Now we still have to distribute the 5. That actually cancels out the 5 that's in the denominator there. So square root of x squared minus 25 plus 5 inverse secant of x over 5 plus c. Okay. So the setup here is slightly different than the last one, where we have x on the hypotenuse rather than the other leg, even though our square root is still on the right hand side. But again, it's just a matter of whatever problem is presented to us, we set it up and we just go from there. That's really the underlying principle that's being used. It's like we use our knowledge of geometry and trigonometry to set up our right triangle here, then create the necessary substitutions from that right triangle, substitute into the identity or the integral, and then simplify, and then whatever's left we then just whatever's there we just integrate the best we can. It may be that it's a simple integral, or maybe that we have to use the principles that we learned in section 2 or 3 of this chapter, depending on how things go. And it's probably not going to be an integration by parts, but it could be like I was talking about. It could be the combinations of secants, tangents, or sines and cosines, like we've been seeing in the previous section 8.3. So let's look at some more. Okay, this will be number 12, which is integral of x cubed over 4 times the square root of 4 plus x squared dx. So we look at our radical. Our radical is 4 plus x squared. I don't know why I put a parenthesis there. Sorry. But we have a sum of two squares is what that amounts to. So if we have a sum of squares, we know that that's going to be our hypotenuse, square root of 4 plus x squared. That means one leg is 2 and the other is x. Now again, I would stress we want 2 on the bottom, and then x would be our vertical side. The reasoning is this. To find, if we want to find x, we want to use x over 2. X over 2 in this case is opposite over adjacent, which is tangent of theta. If we had switched those two and put 2 here and x here instead, we would have adjacent over opposite, which is actually cotangent of x rather than tangent of x. Okay. So we know we're going to use the substitution x equals 2 tangent theta. We also need dx. The derivative of 2 tangent theta is 2 secant squared theta, d theta. And then we also want to pair the square root with the constant side, which is hypotenuse over adjacent. And that is secant of theta when we have hypotenuse over adjacent. So we can say the square root of 4 plus x squared is equal to 2 secant theta. Okay. So that's what we're working with here. Let's make our substitution. We've x cubed on top. Now x, we said, was 2 tangent theta. So that'll be cubed. We also need dx in the numerator, which is 2 secant squared theta d theta. On the bottom we have a 4 times the square root of 4 plus x squared, which we said was 2 secant theta down here. Okay, this one's going to be not going to have things cancel out entirely, which is nice. Working with the constants, we know that we have a 2 cubed, which is 8, times another 2, which is 16. And on the bottom we have 4 times 2, which is 8. I guess this 8 cancels out this 8, and we just have 2 remaining. Okay. We know that one of our secants will cancel out, so 1 secant remains. We also have a tangent cubed. So this problem right here, now that we've done our substitution, it's literally the type of problem we were looking at in section 8.3 at the first part of class today. Now, again, this is the secant tangent case. We had 3 different things we looked at there. The first of those was an even number of secants, and the second of those was an odd number of tangents. So this is our second case for secant and tangent, because we do have an odd number of tangents. So tangent cubed will split up into tangent theta times tangent squared theta, and tangent squared theta will split up into secant squared theta plus 1. Okay. Now, when we were doing the odd number of tangents before, we said we would also take one of our secants. Now, we only have one secant in this case, so we'll just pair that with our tangent. Okay, and then this will be our secant squared theta plus 1. Now, this will be our du, and u will be our secant theta. Du will be our secant theta times tangent theta, which is right here. And so we end up with 2 integral. This is u squared plus 1 du. So this is an interesting problem because we started with the trig substitution and now we've made a u substitution on top of that in order to finally get to a point where we can integrate the expression, which is really the goal here. Is we want to be able to integrate, because once we integrate we can undo whatever substitutions we did in the process. It'll take a while, but we'll get back to the original variable x eventually. So we go ahead and do our integration, which is u to the third over 3 plus u plus c. U, we said, was secant theta. Okay. And now we need to know what secant theta is equal to. Well, we already found what secant theta was equal to in the course of solving the problem. Secant theta is the square root of 4 plus x squared over 2. secant, square root of 4 plus x squared over 2, and that is being cubed, plus 2 times square root of 4 plus x squared, 2. Let's see. Okay. So we plug what the secant is equal to, and now we just kind of simplify what's left over. Now, the 2 cubed on the bottom is an 8, although one of those 2's will cancel out with this 2 here. So it's really 2 over 8, or 1 over 4, so I guess we'll get 1/12. We take that 4 with the 3. And then we have 4 plus x squared to the 3/2 power, because the square root raised to the 3rd power is 3/2. And then the 2's simply cancel here, so we just have plus the square root of 4 plus x squared plus c. Okay, and that'll be our answer in that case. Alright, I went a little longer than I had hoped. Sorry about that. Let me go ahead and write down some homework problems, and that'll be it for today. And we'll revisit this section on next Tuesday for sure, as well as any questions anyone has over the homework. So for homework, we had 2 pages. I'm going to do the second page first, since I'm already on that in the textbook. And I'm just going to do one of each type for y'all. So look at 5. 7 and 11. That's about the extent to which we work those problems already anyway. Eventually we'll have a few more problems there, but for now that's a good start, I think. And then on page 538 before that, go ahead and look at 5, 7. 17. Hmm. 27, 29, 31. And that should be good there. Oh, sorry. So go ahead and look at that for homework. Sorry for keeping you a little bit late today. Hopefully by next Tuesday all the tests will be graded and we can talk about the tests as well. And then also finish this section and go from there. Alright, you all have a good weekend. Take care, and I will talk to you then. Bye.